Welcome back. So, last class we talked about first law of thermodynamics and its limitations. So, the first law of thermodynamics basically states that du is equal to delta q minus delta w, and we saw it has certain limitations, that it cannot predict the direction of a process, it cannot predict the degree of irreversibility of the process, and it does not put any limit on the work to be done. So, these limitations are overcome by the second law of thermodynamics. So, there are various ways to state the second law of thermodynamics, right. One of the ways is, it states that it is not possible to construct a cyclically operating device which will accept some heat from a high temperature reservoir and convert all of it into work. Right. So, such a device is not possible. That is one of the way to state second law. So, what basically this device is doing, it is accepting heat from a high temperature reservoir at T1 and then converting all of it into work. Okay. So, in other way we can state that if we define efficiency of this heat engine as work done divided by heat absorbed. So, the second law states that the efficiency has to be always less than 1, because W has to be less than Q, right. So, now all of the heat accepted cannot be converted into work. So, some of the heat has to be rejected, right, because it is a cyclic process. It has to be a cyclic process. If the heat engine has to operate continuously, it has to be a cyclic process, which means the system has to come back to its original state. So, to come back to its original state, the remaining heat has to be rejected. So, essentially any heat engine that operates, it has to interact with two thermal reservoirs, one from which it accepts heat, then it performs some work W, and the remaining heat is rejected to a low temperature reservoir. Okay. Another way to state the second law is, it is not possible to construct a device which operating in cycle absorbs heat from a low temperature reservoir and transfers it to a high temperature reservoir. So, essentially it is not possible to conduct heat from low temperature to higher temperature without any external influence. Such a device is not possible. So, this is a second way to state the second law of thermodynamics. So, essentially the second law has put a limit on the work to be done, right. The efficiency cannot be 1 or greater, right, it has to be less than 1, and it also establishes the direction. Heat cannot be conducted from low temperature to higher temperature without any external influence. Okay. So, the important consequence of the second law of thermodynamics is that cyclic integral delta Q by T has to be less than 0, right. So, cyclic integral means the integral taken over all the process in a cycle, right. So, if we define a cycle, let us say on a PV diagram, 1 to 2, 2 to 2, 3 and 3 to 1. So, this important inequality, this is called Clausius inequality. This is an important consequence of second law of thermodynamics. If we apply this to the cycle 1, 2, 3 here, what it says is delta q by t is equal to integral 1 to 2 delta q by t plus integral 2 to 3 delta q by t plus integral 3 to 1 delta q by t. This has to be less than or equal to 0. Now, the equality is valid if the cycle is reversible. A reversible cycle means each of the process in the cycle is reversible. So, whole cycle is conducted along an equilibrium surface. In that case, the equality is valid. So, cyclic integral delta q by t is equal to 0 if the cycle is reversible, and the inequality is valid if the cycle is irreversible. The cycle is irreversible if any of the process is irreversible, and this is very important inequality. So, now we can state this as cyclic integral delta q reversible by t equal to 0. Delta q reversible is basically the heat absorbed during a reversible process, or heat effect during a reversible process, right. Now, if we define delta q reversible by t as a variable ds, we can write in cyclic integral ds is equal to 0, and we know this is a property of a state function. Right. So, cyclic integral ds equal to 0 essentially means that the variable s is a state function, and this variable s is called as entropy. So, essentially you can also state the second law of thermodynamics as the entropy is a state function. Now, this gives a very important consequence. If we analyze this inequality further, now we know the definition of entropy. Remember, when we define entropy, we are considering entropy in terms of heat effects. We are considering the reversible processes, right. So, ds is equal to delta q reversible by t. So, if we carry out certain change of state from 1 to 2, the change in entropy 1 to 2 will be S2 minus S1, and in terms of heat effect we define it as delta q reversible by t. So, if we analyze the heat effect of this process 1 2, and if it is reversible, then we can define integral delta q reversible by t is equal to delta s. If we carry out the same state change by another path which is, let us say, irreversible, so let us call this B. So, initial process, let us call it 1A2. Now, 1B2 is an irreversible process. Then we cannot say delta S is equal to delta Q by T, because this is not a reversible path. So, the heat effects will be different. However, entropy is a state function. So, delta is still remains equal to S2 minus S1, because entropy being a state function, the difference delta S will depend only upon the initial and final state. It is not a path function. So, what happens to the heat effects? So, it happens that delta S has to be greater than or equal to integral delta q by t, right. So, equality is valid if the process is reversible and inequality is valid if the process is irreversible. So, if we talk about small differentials, we can essentially write ds is equal to, for any process we can write delta q by t plus some positive quantity, right, because ds is greater than delta q by t. So, ds has to be equal to delta q by t plus some positive quantity, which we denote as ds irreversible, right. So, ds irreversible is a positive quantity greater than or equal to 0. So, again essentially if the process is reversible, then ds irreversible is 0 and we get back the original definition, right, ds is equal to delta q reversible by t. If the process is irreversible, then ds irreversible has to be a positive quantity, which means entropy is produced in an irreversible process. So, this is the entropy produced due to the irreversibility of the process. Now, if we consider an isolated system, an isolated system means it does not interact with surrounding in any way, neither in the form of heat nor in the form of work, right, which means delta q by t is essentially 0. So, ds has to be equal to ds irreversible. ds irreversible is always greater than or equal to 0, which means the entropy of an isolated system can only increase or remain constant. The entropy will increase if the process is an irreversible process. The entropy will remain constant if the process is a reversible process, and this is very important because it helps us to establish the criteria for equilibrium. And what is that criteria? If the entropy can only increase, it can never decrease. So, the equilibrium state should correspond to what? Maximum value of entropy, right, because the equilibrium state is where the system has no desire to change from that state unless acted upon by an external influence. Even if a small perturbance is introduced in the system does not want to change. So, let us see. So, for example, if we consider a process, a reaction A plus B is equal to C plus D, and we want to understand to what extent it will proceed. On the x axis, if we plot the composition of C plus D, right, the left hand y axis is 100% A plus B, right hand y axis is 100% C plus D, and if we see how the entropy changes, and essentially this is carried out in an isolated system, if the reaction is carried out in an isolated system, what happens? Initially the reaction will proceed, right. As the reaction proceeds, the entropy will increase, at some point it will reach a maximum, and then the entropy will start decreasing. Okay, this will be the nature of the curve. So, what happens? Basically there is a maximum on the entropy curve somewhere, and this is the equilibrium state. So, as on the left hand side, as A plus B is reacting to from C plus D, the entropy is increasing, that is possible, it is an irreversible reaction. So, the reaction can proceed, right. When it reach this point, any further reaction would cause a decrease in entropy, right. Now, that is not allowed by second law, because this is an isolated system. So, the decrease in entropy of the system is not allowed. So, the reaction will stop, no further reaction will be possible. Similarly, if we come from right hand side, we start from C plus D, as it reacts to form a little bit of A plus B, the entropy is increasing. So, if we start from pure C plus D, it will react, will form A plus B, and the reaction will continue until you reach this maximum in entropy. Okay. So, this is how we get the criteria for equilibrium. So, the criteria for equilibrium in terms of entropy is, for an isolated system, equilibrium state corresponds to the state of maximum entropy, right. So, as we say isolated system, which means
no transfer of energy and heat.
right. So, basically we are holding internal energy of the system constant and also the volume of the system constant, right. So, U and V are constant. So, you can also say at constant internal energy and volume, the equilibrium state corresponds to the state of maximum entropy, and this is the criteria for equilibrium. This is very important, and we will refer back to the irreversibility when we talk about diffusion with respect to the irreversible thermodynamics. We will try to analyze diffusion process with the theory of irreversible thermodynamics. There, this equation will be very important, because diffusion is accompanied by production of entropy. Okay. So, now we have two laws. The first law states du is equal to delta q minus delta w. The second law states that ds is equal to delta q reversible by t, right. So, if we consider a reversible process and substitute in the first law, we write du is equal to t ds, and delta w we know is p dv. So, this is the combined statement of first and second law of thermodynamics. So, this essentially tells me u is a function of s and v. You can also rearrange this. You can write ds is equal to 1 by t du plus p by t dv, or in other words s is a function of u and v. So, we have already seen when we talk about entropy and want to use entropy as a criteria for equilibrium, we hold u and v constant, right. So, when we use entropy as our state function to define the criteria of equilibrium, we use internal energy and volume as the independent variables. Now, based upon this combined equation, you can also define criteria of equilibrium in terms of internal energy, right. So, in terms of internal energy, the criteria of equilibrium can be defined as follows: at constant entropy and volume, equilibrium state corresponds to minimum value of internal energy. In other words, if we hold entropy and volume of the system constant, then the internal energy of the system can only decrease, it can never increase. Then it is obvious that the equilibrium state will correspond to minimum value of internal energy, because from there the system will have no desire to change in either direction. Okay. So, the second law has helped us to overcome the limitations of first law. So, it has put a limit on the work done, it has defined the direction of the process, and then it has also defined the degree of irreversibility, or to what extent the reaction can occur, as long as the entropy can increase in an isolated system, or as long as the internal energy can decrease in a system with constant S and V. Okay. So, we have now two state variables which we can use to define the equilibrium, but there is a little bit of problem, right. If we use S, we know we need to use U and V as independent variables. If we use internal energy, we need to use S and V as independent variables, and these are not really easy to control, right. Imagine if you want to use internal energy, for example, and I ask you hold the entropy and volume of the system constant. Is it easy to do? No, right. So, we need to define another state variable which can be easily used, or using which we can define the criteria of equilibrium in terms of easily controllable independent variables. For example, temperature and pressure, they are easy to control, right. So, can we define some variable which can define criteria of equilibrium using T and P as independent variables? So, that brings out the question of how do we define the next variables, and that we will talk about in the next class.